Introduction to Poisson distributions in plain English. Today let's talk about what exactly is the Poisson distribution? What's it for? Also, what is its relationship with other distributions? We will not talk about the probability distribution calculation formula at all here, but only talk about the use of this distribution, so don't worry about seeing the mathematical formula. In the natural or humanistic world, we often encounter some events that are independent and rare within a certain time or space. Poisson specially builds models for such events. Once we determine that this kind of event belongs to the Poisson distribution, we can use its formula to calculate the probability of various situations occurring, and then calculate the cost of the event. This plays an absolutely important role in cost analysis of doing business. Which events are independent and infrequent? For example, the number of car accidents at a certain intersection within a year, the number of defective products on the production line within a month, or the number of calls received by the customer service center within an hour. These can all be calculated using Poisson distribution modeling calculations. The Poisson distribution has only one coefficient called lambda, which actually represents the expected value of that event, which is the average number of occurrences. For example, if the customer service center receives 3 calls within an hour, the lambda is equal to 3. If there are 5 car accidents at this intersection within a year, the lambda is equal to 5. After having lambda, what is the actual use of Poisson distribution? We can see that the customer service center can be used to estimate the number of online customer service personnel required, the insurance company can be used to estimate the amount of insurance premiums, and the factory quality control department can increase the selling price of the product based on the proportion of defective products. This is actually very critical to the profit and loss of business. In daily life, Poisson distribution is actually very useful. If there are an average of 3 Uber taxis wandering around within 1 kilometer of your home, lambda equals 3, and when you want to call a taxi, what are the chances that there are none? At this time, you can use the Poisson distribution to calculate the probability that the number of Uber cars is equal to 0. Not mentioning the calculation process, the chance of p(x = 0) is probably less than 5%. As mentioned before, the Poisson distribution can tell us the probability of an infrequently occurring independent event occurring within a certain time and space range. But sometimes what we are more interested in is, when will this event happen again in the future? At this time we have to use another distribution to think about. This distribution is called exponential distribution. For a traffic manager, knowing that the average number of crashes at this intersection is 5 times a year, he would be interested in knowing when the next crash is likely to occur. In the same way, quality control personnel also want to estimate the next time a defect will occur. Insurance company actuaries also want to estimate the next time someone will be in an accident. Regardless of the formula, if the number of car accidents per year at an intersection is equal to 5 according to the model lambda of the Poisson distribution, then according to the exponential distribution, the expected value of the next car accident should be 1/5 years later, which is quite intuitive. Related to the Poisson distribution, here we talk about the most commonly heard binomial distribution, which is constantly throwing dice in experiments. It is actually a distribution that assumes that the probability of success of something is p. After n times of experiments, there is a possibility of k times of success. If there are 10,000 cars passing through an intersection every year, n equals 10,000, and we assume that the probability of success, that is, the probability of an accident when each car passes, is equal to 0.0005, which is 0.05% chance, then we can use the binomial distribution formula to calculate the probability of k, which is the possibility of k accidents. The calculation result should be similar to that calculated using the Poisson distribution. But when n tends to infinity and p tends to 0, the binomial distribution is very complicated and troublesome to calculate. At this time, we can use the Poisson distribution to calculate, as long as lambda equals np is equal to a constant. In the above example, lambda is equal to 5. Therefore, the relationship between the Poisson distribution and the binomial distribution is that when n equals infinite and p equals very small independent events, the problem of the binomial distribution can be calculated by the Poisson distribution. Figure 1 is the probability density function of Poisson distribution, from onlinemathlearning.com, for reference. Figure 2 is the probability density function of binomial distribution, from wallstreetmojo.com, for reference. Figure 3 is the probability density function of exponential distribution, from wallstreetmojo.com, for reference.